Okay, so welcome. My name is Stipsicz Lecture. I'm lecturing now from Budapest, from the Rényi Institute. And this lecture series will be about exotic four manifolds. So let me just recall you what an exotic pair is. So suppose you have two four manifolds, X and Y. And we say that they form an exotic pair if X is homeomorphic. So homeomorphic to Y, so topologically they are the same, but X is not diffeomorphic to Y. So as smooth manifolds, they are different. So in order to address the existence of such pairs, we will need four major steps. We would like to have examples of four manifolds. We will need tools to construct new four manifolds, so some constructions. We will need tools to prove that two resulting constructions give you homeomorphic manifolds. So tools to prove homeomorphism. And then finally, we need tools to prove non-diffeom. Tools to prove that two objects are not the same are typically called invariants. So these will be the sort of the four main guiding principles or ideas throughout the lecture series. So in this first lecture, I would like to give you a vague idea how classification schemes for four manifolds work and what's the status today. So let's start with some basics. So Xn is supposed to be an n-dimensional compact. Most of the time, I will also assume that no boundary. These two properties are assumed, and we call it a closed manifold. And we will also assume that the manifold is smooth and orientable. These two properties can be interpreted by saying that we can cover our manifold with charts where the transition functions are smooth maps and the Jacobians have positive determinants. So that's smooth, being smooth shows that the manifold is a smooth manifold, and the sign of the Jacobian, the determinant of the Jacobian, says that it's orientable. So these are the objects we have. Let me just remind you what happens when the dimension is 0. So there is, one other thing. And we always assume that all manifolds are connected. Otherwise, we can study these objects component-wise. So what happens when n is equal to 0? Then the only such manifold is the point. Suppose we understand the point. When n is equal to 1, then there is one such example, which is the circle. And we are very confident about the topology of the circle. When n is equal to 2, then we have this famous infinite sequence of higher and higher genus surfaces. So it starts with the sphere, the torus, the genus 2 surface, and so on. And the invariant which distinguishes them can be derived from the fundamental group, the first homology, the homology, the total homology, or even it can be captured by a single number, which is called the genus. And from the topological point of view, we do understand the classification, although the theory is not complete. We also would like to understand maps between them, and that is still a source of extensive studies. What happens if we have n equals 3? well, then the theory becomes much more interesting, and it's a very rich theory. And the slogan is that three manifolds are determined by their fundamental group, which is just a slogan. It's not a true statement. And just to see how complicated it can be, imagine that Y is an interesting enough three manifold, and we take the connected sum with itself, or we take Y with the connected sum of the same manifold with the opposite orientation. Clearly, the fundamental groups will be the same, but the two three manifolds might be very different if Y is complicated enough. So, you know, this is just, let me put it in quotation mark. It is some philosophical level, it is true, but as a true mathematical statement, it's absolutely false. But still, the most important information about the three manifold is captured by the fundamental group. In some way, this is a generalization of the two-dimensional case. And remember the famous conjecture stating, which is now a theorem, stating that if pi1 of Y is trivial, so we have a three-dimensional manifold which is closed, smooth, orientable, and connected, and moreover, it's simply connected, then it should be the three-sphere. So this was Poincaré's conjecture now, which has been resolved by Perelman 20 years ago, almost 20 years ago. And I think this is that much I would like to say about three manifolds. And now we move to four dimensions. Let me add one more sentence. The fundamental groups of three manifolds are very special. So they form a very special subclass of groups. What happens in dimension 4? So let me start with a fact. If G is a finitely presented group, then there is a four manifold X4 satisfying the previous conditions that it's smooth, it's orientable, and so on, such that pi1 of X is isomorphic to G. So in contrast to the three-dimensional case, every group will appear as a fundamental group. And we know that deciding isomorphisms of variously presented groups is a algorithmically not solvable problem. So fundamental groups might really cause a major headache here. So what do we do in this case? Well, we assume that the fundamental group is trivial. So from now on, assume I1X is trivial. I will not always stick to this convention. Whenever I do not, then I will emphasize that, but most of our objects will be simply connected. Notice that in the light of Poincaré's conjecture, if this would hold, then we would get a very simple theory, but it's by far not true. Simply connected four manifolds form a very large class of objects, and we are only dreaming about sort of understanding them completely, as I will try to emphasize in these lectures. So, very well. So in the line of arguments which I showed for 2 and 3 manifolds, there is some variant of that, the following theorem of Freedom, 1992, says the following, that smooth manifolds, four manifolds, simply connected smooth four manifolds, can be classified up to homeomorphism. So here is the theorem. So X1, X2, smooth, simply connected four manifolds homeomorphic and only if their cohomology rings are isomorphic. As rings. So we have to remember that homology is typically a group, but when we study cohomologies, there is a cup product operation which turns it into a ring. And here the property we demand is that these two cohomology rings should be isomorphic. Notice that this direction is standard fact. If we have homeomorphic spaces, then the cohomology rings are isomorphic. In fact, we need less from the spaces. If they are homotopy equivalent, then the cohomology rings are isomorphic. The real work of Friedman is the converse. So this is easy, and this is very hot. This granted a Fields Medal for Friedman in 1986.
You can draw school.
So if there is a version for topological form manifolds, which is a little bit more complicated. So what I would like to emphasize in this picture is that we talk about smooth manifolds up to homeomorphism. So there is somehow a clash of categories, and this will sort of an underlying theme that topological properties of smooth form manifolds are easier to understand, and we would like to substitute this property with diffeomorphism. Then the classification scheme will probably be very complicated. At this moment, we have no idea how complicated it will be. So there is very little knowledge about the classification of smooth form manifolds up to diffeomorphism. Okay, so let me add one more remark that so here we demand the cohomologies being isomorphic as rings. What if we drop that and we only want to demand that the cohomologies are isomorphic as groups? Well, then the whole theory collapses. For example, S2 cross S2, fantastic simply connected smooth form manifold, and CP2 connected sum, so the complex projective plane connected sum with itself with the reverse orientation. They do have the same cohomology groups, but their ring structure is different. So, and we will later on discuss why these two guys are not even homeomorphic. It will not be very complicated. So we really need this adjective, you know, it's a ring homomorphism, it's a ring isomorphism, not just a group. Okay, so, well, let me elaborate a little bit about the cohomology ring of a simply connected form manifold. So, well, what is the cohomology ring of X? Well, this is a simply connected form manifold. So we have H0, is isomorphic to Z, and then we don't have H1 because it's simply connected, so the first homology and first cohomology vanishes. We do have H2. Then we don't have H3, again, because H1 is 0, and there is pointary duality, so H3 is also 0, and we have H4, which is isomorphic to Z. And notice that we always assume that our objects are not only orientable, but indeed oriented, which means that we do have an identification of the fourth cohomology with Z, likewise the zeroth cohomology with Z. So these are like fixed isomorphisms because of the orientation. Okay, so this is the scheme as a group, and the ring structure, the cup product, maps from H2 to H4. So it assigns for two cohomology classes the cup product. And using this, we can turn this map into a symmetric bilinear form. So Qx is defined as follows. We take A and B, and we associate to the pairing between the cup product four-dimensional cohomology against the fundamental class of the oriented four manifold. So this ends up being an integer. And from basic theory, it's not very hard to see that this is a symmetric product because these are two-dimensional classes. And also by Poincaré duality, we can confirm that this is a unimodular form, which means that in a basis, when you write out as a matrix, it will have determinant plus or minus 1. So this is a bilinear, symmetric, unimodular form. And notice that this is essentially the information we get out of the ring structure of H upper star, because everything is completely determined. H0 and H4 are determined, and this captures H upper 2 together with the ring structure. So this is really, when we talk about the cohomology as a ring, we can sort of substitute it with that single symmetric bilinear form, which is called the intersection form. So let me just. So Qx is the intersection form of the four manifold X. Okay, why is it called an intersection form? So it is a fact that QXAB can be determined by taking sigma A and sigma B, which are two-dimensional homology classes, surfaces representing homology classes, the Poincaré dual of A and the Poincaré dual of B, and we take the intersection and count the number of intersections with signs. So this is a sort of a long sentence, and I will not completely unpack it, but the picture you have to have in mind is that when you have a two-dimensional cohomology for a four-dimensional manifold, then you can represent the Poincaré dual of it, which is now a two-dimensional homology, by an embedded oriented surface, which for A I denoted by sigma A, and you have to take two of those, sigma A and sigma B. Unfortunately, I don't have enough dimension on the blackboard to indicate that two-dimensional objects intersect each other generically in finitely many points. And at each intersection point, you assign a sign, whether the orientation of the first concatenated with the orientation of the second gives the orientation of the four manifold. You sum up these signs, and that will be the intersection number. And the statement is that this is true. So here's the whole first homework assignment. Show that for A in the second homology, the four manifold, the Poincaré dual can be represented by a smooth, orientable surface, two real dimensional surface, meaning that the image under the embedding of the fundamental class of this surface is exactly the Poincaré dual homology class. Okay? All right, so this is why Q is called the intersection form. It has something to do with the intersections of surfaces representing homologies. All right, so when we would like to understand the cohomology rings which appear in Friedman's theorem, what we really would like to understand is these symmetric bilinear forms. So let's turn to algebra for a few minutes and try to understand how many such objects we have. And as I already remarked, if you pick a basis of H2, you can represent these objects by matrices. But of course, different matrices can represent the same form. So we have to understand this equivalence relation a little better. And so I will which again comes from linear algebra and from number theory. Because notice the peculiar point, we are not taking this intersection forms over fields. We are taking it over Z, which brings a little bit of a complication in the story. Nevertheless, here is the theorem. So there are three invariants of such a symmetric bilinear form, which I will denote by Q from now on. It does not have to come from a smooth four manifold. It can be an algebraic object by itself. And so the three invariants are the following. So there is the rank of Q, which is just the rank of the free abelian group. It is defined on. So in our case, in the smooth four manifold case, it's just the second Betti number of X. So that's an integer. There is the signature of Q, which is defined in the following way. So if you have an intersection form over Z, then you can consider the same intersection form over R. And we did learn in school that every symmetric bilinear form can be diagonalized over R, and you will have some number of ones and some number of minus ones in the diagonal. When in the most general setting in this Sylvester theorem, you are also having zeros in the diagonal, but since we have unimodular forms, so they are non-degenerate in particular, you only have ones and minus ones. And so this is the difference of B2 plus and B2 minus, where this is the number of plus ones in the diagonal, after diagonalizing over R. And this is the same, but the number of minus ones. And Sylvester's theorem says that it does not matter how you pick the new basis in which your form is diagonal. You will always have the same number of plus ones and the same number of minus ones. So their difference, or said differently, the trace of a matrix in that basis is exactly the signature. And finally, there is a one, so this is now an integer, which obviously might be negative. And we say that Q is even if QXX is even for every X and all otherwise. So this is like a 0 or 1 type of property, even or odd. Notice that this is where we use that or intersection form or bilinear form is over the integers and not over the rationals or the reals over the field, because that makes no sense whatsoever over those fields. Okay, so So here is the theorem, which again is a combination of number theory and algebra. So theorem, first case, if Q is indefinite, X and Y such that QXX is negative and QYY is positive, then
Andras,
yes,
it's slightly outside the camera sight on the right.
Okay. So if there are different signs of squares, then we have the following. Then these three numerical invariants completely classify Q, and in that, indeed, Q is equal to or equivalent to the following form. It can be represented in an appropriate basis by a diagonal matrix, where in the diagonal we have n ones and n minus ones. This symbolizes the one-dimensional form having a single one. And when I put a number in front, I imagine that I take the direct sum of those. So this corresponds to the matrix n ones and zeros everywhere, and then n minus ones and zeros everywhere else. So this is very simple, and we can read off, for example, the rank of this intersection form is n plus m, the signature is n minus m, and it's an odd intersection form because there are elements which have square 1 and square minus 1. Or Q is equivalent to some number times the E8 form and some other number times 2 by 2 form, which I will define in a moment. So H can be given by this very simple 2 by 2 matrix. It's called a hyperbolic pair. So this is why we denote it by H. And E8 is an 8 by 8 matrix. So I will not draw that because it would take forever and I would definitely make a mistake. But it can be specified by a single graph. And I will draw the graph. 1, 2, 3, 4, 5, 6, 7, 8. And so how do we make an 8 by 8 matrix out of that? We just take 8 basis vectors, and in the diagonal, we put all -2s, and in the off diagonals, we put a 1 if the corresponding 2 vertices are connected, and we put a 0 if they are not connected. So I advise you once in your life to write down that matrix, but never do it again. This is a much more compact way to capture. So again, what I have here is a block matrix. You have E8, some of them, exactly n of them, and then it is followed by L copies of H. Now, n and L can be integers. So when I have n is -5, by this I mean that I take the E8 matrix where all the signs are reversed, and I take it 5 times. Okay, so this is even and this is odd. It needs a little bit of a thinking, and I advise you to think that an intersection form is even if and only if in a matrix presentation, the diagonal contains only even numbers. And here this is clearly true because we have zeros and -2s in the diagonal, and so this will be an even form. This boils down to our sweet high school memories that the square of a sum is the individual squares plus twice the mixed ones. So mod 2, they sort of don't count. Okay, so this is what we have. And so this is what we have for the indefinite case. Let me finish the theorem. If Q is definite for a fixed rank, there are only finitely many different Qs. But this number can be very large. For example, for rank 40, there are, I don't know, at least 10 to the 50, something like that. I don't want to impress you with these numbers, like there are more intersection forms than the atoms in the universe or stuff like that. But there are many, including 2, the n times the plus 1. So this is a prototype positive definite intersection form or bilinear form, and a prototype negative definite when you have only -1s in the diagonal. But those are just 2 out of this zoo of a very complicated zoo of symmetric bilinear forms. Notice that this first theorem just says that Q in the case of in the indefinite case is determined by the parity, the rank, and the signature. Right? Here the rank is n plus n, and the signature is n minus n. And clearly, once you tell me what the rank and the signature is, you can recover n and m. It's a very simple linear system. Here the rank is 8n plus 2l, the absolute values. And the signature is minus 8n. So once again, from the rank and the signature, you can recover what it is. And for the indefinite case, we don't have that.
So, sorry, I just realized if L is 0, then the Q, which is equal to NE8 plus LH, just NE8 by itself is definite, right?
E8 is definite, and this is not definite.
But okay, so you need L to be different from 0 if you want this to be.
Yes.
Okay, I see. But actually, you should write N, I guess, instead of Z. But I mean, it's clear what you mean.
So L, you can always take L to be positive, but N, you might not. So maybe a more precise.
What does it mean? Minus
N is
1
from Z.
Okay, yeah.
L is from N minus 0.
I see.
Yeah,
and if you put a minus in front of EH, you just change all the signs of the matrix.
Yeah, here.
Okay, yeah.
Yes.
Okay.
So for age or minus age is the same. So it doesn't make a difference. Okay, so this is what we have from algebra. So, you know, it looked like a zoo, but now our understanding should be that for the indefinite case, we really need rank, signature, and parity. For the definite case, we are still in the wild, and we don't know. So here are the, okay, this is from algebra. This is what happens with the intersection forms. What happens with smooth manifolds? So I will give you a sequence of theorems just to orient you. We will not prove these theorems, obviously. And so I will attribute it to Rocklin, Donaldson, and Furuta. And this will be a multi-level theorem, and I will always put the initial who actually proved that particular statement. And so here's the first one. So Rocklin said the following, that if X is smooth, simply connected, and QX is even, just a side note, and we will come back to that later on, this just implies that X is a spin manifold. And we will discuss this spinness in lecture 3 or 4. Then the signature is divisible by 16. So notice that Q is even, then the signature is always divisible by 8. And now this comes from algebra, and differential topology says that you can improve it by a little bit, not only 8 by 16. Said differently, for a smooth manifold, the coefficient of E8 should be always an even number. There are two conditions, even and smooth. If you draw any of those, the theorem, as you might predict, completely collapses. Okay, so that was Brocklin's theorem from the 1950s, and this was sort of the first very strict restriction on the topology of smooth four manifolds. And then in the early 1980s, Donaldson shot the topological work by the following theorem, that if Qx is definite for a smooth four manifold, and of course, there is a version for positive definite and for negative definite. So let me just say that if it's positive definite, then Qx is just this very nice diagonal form. If we assume that Qx is negative definite, then it will be m times the minus 1. So what does this send us? What's the message it sends us? Well, in the definite case, the intersection forms or the potential cohomology rings are messy. There are a lot of possibilities, but only two of them, for the positive definite one, this one, and for the negative definite one, its little brother, those arise as intersection forms of smooth four manifolds. And as always, all manifolds are closed, simply connected, oriented, and so on. Okay, so that's sort of a good news. So if we combine these theorems, I would like to continue on. So around the same time, Donaldson proved the following. So if Qx is even and B2 plus is at least 2, then at most 2, then Qx is just H or 2H. So notice that, suppose we are taking the case when E8 is the negative definite and N is positive. So this portion only gives negative terms to the signature. So all the B plus comes from this side. And it just says that if we have 1 or 2 positive eigenvalues, then it can happen only by having an H and a 2H. For example, this is not possible, right? E8 plus H, say. Or actually, this is already forbade by Rockley, but say this one is not possible. So this last bit has been improved a little bit by, well, not a little bit, significantly by Furuta, saying the following. Furuta, if Qx is even, and as always, X is a simply connected closed smooth four manifold, with Qx 2n E8 plus LH, then L should be at least, how is it? 2 and absolute gravity. So this is clearly a generalization of Donaldson's previous theorem. And the conjecture is that indeed L should be at least 3 times the absolute value of n. This conjecture is called the 11/8 conjecture. And this statement is the 10/8 theorem. And I will not elaborate on y11 and y8, but if you work it out in terms of signature and Euler characteristic, then you will get exactly these numbers. Okay, so this is where we are, and so we can summarize in the following, what I said so far in the following theorem. So this is a combination of Friedman and Donaldson, saying the following, that x1, x2, 2, smooth, simply connected, closed form manifolds. Are homeomorphic if and only if we have the following 3 conditions: that d2 of x1 equals d2 of x2, which, since the 0th and the 4th homologies are always the same and there are no first and third, which is equivalent to saying that the Euler characteristic of x1 is the same as the Euler characteristic of x2. This is one condition. And the second is that the signatures should be the same. And they have the same type. x1 and x2 are even at the same time. So either both are even or both are odd. Shortly, their type, the evenness or oddness, is the same. So that sort of answers how to test whether 2 form manifolds are homeomorphic, right? We have to check, we do all kinds of constructions, then we have to check that we are still in the smooth category. That is, depending on what operations we do, we will do always smooth operations. We have to check that the end results are simply connected, so they have the same fundamental group at least, and that happens to be the trivial group. And then we have to compute the Euler characteristics, the signatures, and verify that they have the same type. These are clearly necessary conditions, and the combination of the theorem of Friedman and Donaldson say that they are indeed sufficient. So it's a very abstract way of producing a homeomorphism. You don't see the homeomorphism at all, but the theorem tells you that there is one. Indeed, this is the topic which will be touched upon by the lecture series of Aru. So we will learn some bits of Friedman's theorem from her lectures.
Okay, Andras, can you repeat quickly what you mean by even at the same time? I thought
so
even
either
was the binary condition.
Either both are even or both are odd.
Ah, okay.
So they should have the same type. I mean, this is clearly a necessary condition for the rings, the cohomology rings, to be isomorphic. Either all squares are even in both, or there are odd squares in both. And it's sort of a surprising result that there are these 2 sort of easy to control weak numerical invariants, and there is a 0 or 1 property, and that's enough for homeomorphism. Okay, so let me make a few remarks. So here is the conjecture, the 11th conjecture. So what happens regarding examples? Well, I claim that if Q is odd, and by the theorem it says that it's the same as the diagonal form with ones and minus ones in the diagonal, then there is indeed a smooth, simply connected, closed four manifold with Qx being exactly Q, and this X can be taken to be n copies of CP2 connect summed to each other, and then connected some n copies of CP2 with the orientation opposite to the complex one. So when you have an odd indefinite intersection form or an odd definite, which is allowed by Donaldson's theorem, then those forms actually come up. They are realized. If Q is even, and again, allowed by the obstructions I listed by Donaldson's theorem, by Rockley's, all these, so it looks like 2n times dA plus L times H, then n copies of the K3 surface connected some with L minus 3n copies of S2 cross S2 realizes that provided Cal is at least 3n. So if this Q satisfies the conclusion of the 11.8 conjecture, then it can be realized by a smooth manifold. We will discuss what the K3 surface is later on, and the intersection form of the K3 surface is just 2E8 plus 3H. So this is where it absorbs the signature, and then it takes up n copies, 3n copies of H. What happens between Fruta's result and the 11.8 conjecture, we don't know. Whether there are such four manifolds, we don't know. Indeed, there are epsilon improvements of Fruta's result, so you can add some constants to this 2n every now and then. So it's very likely that maybe the 11.8 conjecture is true. On the other hand, the methods of Fruta stop after these epsilon improvements. So we don't know. That's definitely a very interesting question. Let me add two homework assignments here. Homework, show that the intersection form of a connected sum is just the sum of these intersection forms. This is what I repeatedly used before. Please think it over. It's not very complicated. And the other is that I sort of indicated that for definite forms, the rank, signature, and parity does not classify. Well, how can you show that? Let me give you an example. Let's take E8, the negative definite 8 by 8, and add -1. So it's a 9 by 9 matrix where you have the 8 by 8 piece from the E8, and then you put a -1 and those zeros. And take 9 times -1. These are two 9 by 9 symmetric bilinear forms. They have the same rank, the same signature. They are both odd. So what we learned from the indefinite case, they should be the same. Show that they are not. There is no base change which can transform one into the other. Okay, so it does not verify that there are a lot, but it does verify that there are more than one. Okay? All right, so, all right. Good. So this will be our tool to prove that results of certain constructions are homeomorphic. We will use always this theorem of what I attributed to Donaldson and Friedman, saying that we only have to check the Euler characteristic, the signature, and the type. And of course, before doing that, we have to check that we are dealing with simply connected four manifolds. So that's the plan. And now I would like to talk a little bit about constructing four manifolds. So constructions. So there is an overall construction we will use on and off, and I will just set up the basic theory, and then in Lisa Piccirillo's lecture series, there will be some elaboration on that. And the whole thing relies on handle calculus. So what is a handle? So definition, an n-dimensional k-handle is the k-dimensional disk cross the n minus k-dimensional disk, or, you know, from CW complex theory, we just take a K cell, but we sort of fatten it up until it looks like an n-dimensional manifold, glued to an n-dimensional manifold with boundary along. So we are not using the entire boundary of this guy, we sort of use half of it. So we glue it along this portion. So if you would like to make a picture of that, then it's like dk in this direction and dn minus k in the other direction. So there is a k-dimensional disk, and it is sort of upgraded to an n-dimensional manifold, and we just take the boundary of dk, and we glue along that boundary, along that portion of the boundary. And we will not touch this portion of the boundary. Okay, so of course this is just sk minus 1 cross dn minus k inside the boundary of this n-dimensional manifold, which I will now denote by x. So in order to specify the gluing, we have to identify a k minus 1 dimensional sphere inside here, which has a trivial normal bundle, but we need a little more. We need a trivialized normal bundle. So we might ask, you know, how many sk minus 1s we have? This is a kind of a knot theory question. So inside this n minus 1 dimensional manifold, we are looking for k minus 1 dimensional knots with the property that they have a trivial normal bundle. And indeed, we have to fix some kind of a trivialization of the normal bundle. You might ask how many trivializations we have, and the trivializations are parameterized by k minus 1 O n minus k. So I will not explain that. You just have to think a little bit. If you have two trivializations, then over every point of sk minus 1, you have a base change of this n minus k dimensional space. So if you go around the entire sphere, you will get an element there. So what happens for four manifolds? So how to start this whole procedure? Well, let's see what happens if you would like to use we would like to attach a zero handle. So zero handle is D0 times D4 attached along the boundary of D0 across D4, which is just the empty set. So when you would like to construct a four-manifold, you can start with the empty set and you attach the zero handle to the empty set. You know, in Bible terminology, this would be like creation. Like there was nothing and suddenly there is a zero handle. In my mind, it always looks like something like that. Of course, this whole theory corresponds to Morse theory, and the zero handles correspond to the minima of Morse functions. So, you know, this is the good picture for that. And now I make a few statements. So we can always assume that for X connected and closed as always, oriented, we need a single zero handle and a single four handle. That's just to say that we can change the Morse function to have one absolute minimum and one absolute maximum. Sorry, one local minimum and one local maximum. Okay. The framing, so this trivialization, the framing, i.e. the trivialization of the normal bundle is unique except when K is equal to 2. So for 0, 1, 3, and 4 handles, the framing is unique. And for 2 handles, it's not. This group actually time 1 of S, O, how much is that? 2. It's just Z. So there are a Z worth of trivializations of a knot of a one-dimensional sphere inside a three-manifold. So
can you explain why O became S?
Yeah, well, for pi 1, you know, it only studies one component, and we always take, for the Lie group, we always take the component containing the identity. So it will be SO. For a one handle, this might make a difference when we are studying pi 0, and this is sort of taken away by assuming that we are taking only oriented four manifolds, as we do throughout. Okay. So most of the time, we only have to record the sphere with a trivial normal bundle. We don't have to worry about the actual trivialization because it is unique, except when K is 2, so we have 2 handles, where an additional integer will help us determining which trivialization to do. Okay. And what else do I want to say? And here's a fact. The theomorphism of the connected sum of K copies of S1 plus S2 extends to a diffeomorphism of the boundary connected sum of K copies of S1 cross B3. So this is a 4-dimensional manifold, S1 cross B3, and you sort of boundary connect sum them. You have a 4-dimensional manifold with boundary. The boundary will be the connected sum of S1 cross S2s. And if you pick a diffeomorphism here, then the fact, it's a theorem actually of Lauterbach and Cohen-Haru, tells us that this diffeomorphism extends. this doesn't seem very relevant at the moment, but then here is the principle. So another fact, the union of the zero handle and K1 handles, it's not very hard to see that this will be exactly K times S1 plus D3, which is also equal to the union of the 4 handle and K3 handles. Notice that there is this duality. If you take a Morse function and suddenly you replace it with minus the Morse function, then everything stays the same except what used to be 0 handle becomes 4, what used to be 1 becomes 3. So there is this thing, and the 2 handles sort of turn into themselves. So we cannot really capitalize that on them. And so this is what we would like to symbolize. So what we learned from these two facts above is that if we know how to build up a 4 manifold using 0, 1, and 2 handles, then the rest is somehow unique, because the rest would be 3 handles and 4 handles, which is a standard manifold. And how we glue, it's completely uninteresting, because whichever gluing we take of the boundary, 2 different gluings will give you diffeomorphic results. So what we really have to record is what are the 0, 1, and 2 handles. There is a single 0 handle. This is D4 in the space with the boundary S3 we are living in. Well, your impression might be that we are living in R3, and this is true, but there is a point at infinity which turns it into S3. And so here is my statement. So suppose that X is a 4 manifold, now with boundary, which is built using a single 0 handle, some 1 handles, and some 2 handles. X can be symbolized as follows. Let's take a link L in S3. So it's a multi-component knot, which decomposes as L naught union L1 union L2, where L1 is an L component unlinked, so these are unknots which are not linked to each other at all. So this is a simple picture, and we put a dot on each. So it will look like this, and L2 is a link with each component is equipped with an equilibrium. So, in short, we can say that it's a frame link. So how does it determine X? Well, as I already referred to, this S3 is assumed to be the boundary of D4. This is our 0 handle. And then there are these unknowns in as L1. So this is one of them. So L1 is just L1 up to L. So L, this is one of them. These two dots symbolizes the first node in that link. This is an unknot bounding a disk. It bounds this disk. So we take this disk, which lives in S3, we push it into D4, like this, and we delete a tubular neighborhood of it. So we just take a tubular neighborhood and we delete that. In my picture, it seems like it cuts the boundary into two components, this one and this one. But you have to remember that this circle is a three-dimensional sphere, and these two dots symbolize a one-dimensional circle, and this arc is a two-dimensional disk, so it's sort of carved out. So you can say that this is like a two-dimensional disk worth of antimatter. It's like you cannot go there, it's not there. So you do it for every component of L1, you cut this out. And then you have components of boldface L2, which are framed nodes. So there is a component like this, which might be linked, and this can be a very complicated knot. Say, my favorite complicated knot is, of course, the travel. So it can look like this. It is linked to one component of boldface L1, and then it comes with a number. There is a frame. So you take the normal bundle dictated by this frame, and then you attach four-dimensional two-handle along that. So this is how you build up from that information an X. And if the boundary of the result turns out to be a connected sum of S1 cross S2s, then you close it with 3 and 4 handles. Otherwise, you don't have a closed form manifold. So this is sort of a combinatorial link theoretic way of specifying four manifolds. And let me finish by assigning a homework problem. Suppose X is given X closed, four manifold is given by L, satisfying two properties, that L1 is empty, and then the boundary of when you run through this algorithm and you don't finish, this happens to be S3. So this is the zero-fold connected sum of K S1 cross S2s. Then QX, this famous intersection form, can be easily read off from this picture, is just the linking matrix of L2, where different components link according to the linking number, and in the diagonal you put the framings. The framings in the diagonal. So this is what I wanted to say today. You can represent four manifolds through these links. Of course, this is never unique, and you can ask, when does that happen, that two different presentations of the same four manifold? How can we relate two different presentations? And that's the subject of Kirby calculus. These are called Kirby diagrams, and that notion will be touched upon by Lisa's lectures. So you have to wait for that. That's it for today. Thank you very much.